Hi, this is Yingzhen Li from Imperial College London. I'm broadly interested in publishing machine learning, and today it's my great pleasure and honor to discuss with you my research on how to make deep learning models more robust and adaptive. Now it's the beginning of 2023, where the world is hopefully starting to get out of the global pandemic. But for many people, the world is still in a state of upheaval and uncertainty, which is difficult to cope with. On the other hand, thanks to the advances in technology, the global society is capable of coordinating responses to the challenges. Given that now we have a lot of exciting AI technologies and a tremendous amount of data, it seems to us that AI-assisted decision-making is promising to help us navigate through this uncertain time. Indeed, from text and image generation to protein folding and weather forecast, deep learning systems are making amazing progresses that have wowed many of us. A key factor for these achievements is the availability of gigantic amounts of structured data for the neural networks to exploit. It sounds great if we can apply these deep learning systems to help us make decisions. Unfortunately, these success stories are difficult to replicate if we look at a broader set of business and public sectors beyond tech. The reason is exactly the lack of big and structured data. For people in hospitals, factories, or even government departments, the data they deal with is mostly tabular data, with no clear structure and thousands of entries per table on average. Pre-training techniques are not applicable here, and neural network performances are not particularly outstanding in these applications. But more importantly, accurate prediction is not enough for an AI system to be trustworthy and useful for decision making, and our users want much more. There are a lot of requirements for a trustworthy AI system. Two of them are worth highlighting in my opinion. First, it is necessary to consider uncertainty when making decisions, especially when bad decisions can lead to disastrous outcomes. So the machine learning model needs to be able to describe its uncertainty in a reliable way. Second, as we deploy our AI system during time, the test environment can change and the model can make mistakes. So the model needs to be able to adapt and learn in a continual fashion to suit the changing needs from the users. In this talk, I'm going to briefly show you how we can apply Bayesian machine learning to address these two requirements. In Bayesian inference, we want to infer the unknowns from data with uncertainty estimates. More specifically, we build a model with parameters theta and maintain a posterior belief of all possible theta given data. This posterior distribution not only tells us which theta is most likely to explain our data, but also represents our uncertainty of the inference results. This Bayes rule from the 18th century is at the core of Bayesian modeling techniques even until today. Let's see how this Bayesian modeling principle applies to neural networks. Say we want to build a neural net to classify animal images. Typical deep learning approaches learn the neural network parameters theta using maximum likelihood. In the classification example, we often use the cross-entropy loss, which corresponds to maximum likelihood training with categorical distribution as the likelihood. After training, in prediction, when a new input x star arrives, we use the fitted parameter theta star to compute the network prediction y star. But for Bayesian neural networks, we will first define a prior distribution on the network parameters, say a flat Gaussian. Then, given training data, we will compute the posterior distribution of the weights using Bayes' rule. In prediction time, given a new image, we do Bayesian predictive inference by averaging the prediction outcome of the neural networks using different parameters. And the weighting for each of the weights is determined by the posterior. That's the ideal setup, but unfortunately, the posterior distribution is intractable. In practice, what people do is to first find an approximate posterior Q that somehow approximates the exact posterior P well. Then in prediction time, we compute the random ensemble by sampling k sets of parameters from Q and averaging their prediction outcomes. Therefore, approximation quality is key to the performance of Bayesian neural networks. But let's see how we can get a Q distribution in the first place. In approximate inference, what we want is to find an approximate posterior Q in a distribution family to approximate the exact posterior P by minimizing some divergence. For now, I'm going to assume the Q distribution to be a mean-field Gaussian distribution. Then we just need to choose a divergence. A popular choice here is the KL divergence, which is defined as the expectation of the log density ratio under Q. But the main problem is that the exact posterior P is intractable, so that this KL is also intractable. Fortunately, we can show that minimizing the KL is equivalent to maximizing the evidence lower bound, or elbow, which is derived by subtracting the KL from the log marginal likelihood. Here, the log marginal likelihood is a constant with respect to Q, so it doesn't matter. In the final form of the elbow, what we need is just the joint distribution, which is often tractable. So this is great. We can do Bayesian inference to find posterior approximations. But there is a catch here. Variational inference with KL often returns overconfident posterior approximations. This is due to the zero-forcing behavior of minimizing KL QP, which wants Q to have low density whenever P has low density. On the right, I'm visualizing the mean-field variational approximation results for a Bayesian linear regression model. You can see that when the exact posterior gets more correlated, the variation posterior becomes more overconfident, which is not what we want. Since the problem comes from the usage of KL, one way to fix it is to consider other divergences. In this case, I'm going to use Renyi's alpha divergence as defined on the slide. It contains a lot of interesting special cases, such as the KL divergence itself if we take the limits of alpha to 1, and also some other useful divergences like Hellinger distance. This means we can choose one of them to suit our need, but remember the exact posterior P is intractable, so that we still cannot compute these divergences. But let me remind you again about how we solve this problem for KL. We can do exactly the same thing for Renyi divergence by subtracting the chosen Renyi divergence from the log marginal likelihood. In the resulting bound, what we need is again just the joint distribution, which is tractable. By applying Monte Carlo and stochastic optimization techniques, we can make the VR bound optimization as tractable as optimizing the elbow. So now we have more choices of divergences for posterior approximations. Let's go back to the Bayesian linear regression problem again, and we start from the KL divergence solution in purple. Now let's try to reduce the alpha values. And the corresponding approximation becomes more and more conservative, until alpha goes to minus infinity, which returns the most conservative estimate that covers a lot of low-density regions of P. On the other hand, we can also try larger alpha values. In particular, when alpha goes to plus infinity, we will get the most optimistic estimate of the Q distribution. But even so, it still maintains some uncertainty, unlike point estimate methods such as MAP. This means we can tune the alpha values to achieve the desired uncertainty behavior we want for the downstream tasks. Now let's see how our method works in practice. Here's an example of defending adversarial attacks. In this case, we train a deterministic NLP and also 3 Bayesian neural networks using Renyi divergence of different alpha values. And these methods correspond to different approximate inference approaches. First, we see that the Bayesian neural networks are more robust than the deterministic NLP, where mask covering posterior approximation provides further improvements. We also plot the predictive entropy as an uncertainty measure, and it's clear that the Bayesian neural networks are uncertain about their prediction results. We further test a targeted attack that tries to fool the networks for classifying digit 7 as 0. Again, Bayesian neural networks are more robust, but interestingly, as we increase the perturbation strength, the resulting adversarial images for the Bayesian neural networks look closer to digit 0. And in this case, the Bayesian neural networks become more and more confident about their prediction as digit 0. This shows the Bayesian neural network posterior has covered a lot of interesting solutions. As a quick summary, Renyi divergence Variational inference is a unifying and scalable approximate inference framework that contains lots of interesting algorithms as special cases. By choosing suitable alpha values, we can obtain better uncertainty estimate results. Lots of people have tried out this framework in different applications, so you can also have a go if interested. We've seen how we can get Bayesian neural networks running for predictions and uncertainty estimates. Now let's talk about the second requirement of adaptive learning, and the way to achieve this is via continual learning. In continual learning, we would like to learn a model on a number of datasets coming from different tasks. In particular, the datasets arrive in an online fashion so that we cannot revisit historical data. The goal here is to train a good model on this data stream so that it performs well on all the tasks that we have seen. This setting is extremely flexible. For example, we can have different tasks. We might not know the task boundary, and the dataset size for each task can be quite different. Now, let's build a model for all the tasks. This model has a shared parameter phi, as well as task-specific parameters phi k. Let's first imagine we can use all the datasets at the same time to compute the posterior. There is no forgetting issue here, so this scenario can be viewed as an oracle. Now, if you look at the terms highlighted in cyan, it's actually proportional to the posterior distribution after observing k-1 tasks. So this leads to an equivalent expression of the posterior after observing k tasks, which is proportional to the product of the likelihood for the k task in red, the previous posterior in cyan, and the prior over the current task specific parameter phi k in blue. This is exactly the update rule for online Bayesian inference, which keeps on updating the posterior as the way to maintain historical information. Therefore, we can do online Bayesian inference for continual learning, and it has the same performance as the oracle if we can do exact posterior inference. Unfortunately, we cannot do exact posterior inference. So in practice, we replace the exact posterior distributions with approximations. This means the previous approximate posterior will be used as the prior for the current task, and we will run approximate inference again to update the Q distribution. The Q posterior can be obtained using any approximate inference method. Furthermore, if we use factorized Q distributions, then the two distributions in the divergence term have a lot of common terms that can be cancelled out. So in the end, what we need is the approximate posterior for the shared parameter phi and the prior for the task-specific parameter phi k. After seeing data for the k task, we will obtain the latest Q distribution for phi and phi k, and there is no need to revisit the task-specific parameters for previous tasks. Let's see how this Bayesian framework works in practice. Here, we consider the SplitMNIST benchmark, which has 5 binary classification tasks on different digits. We compare a number of different approaches, including variational continual learning, which uses Variational Inference as the approximate inference algorithm. We see that overall, VCL performs very well in remembering previous tasks. We can further improve VCL's performance by adding a small amount of memory and performing suitable corrections. Notice that using coset only does not perform very well, so this means the online Bayesian inference approach is necessary here. We also test the continual learning methods on image generation tasks, where each task corresponds to generating images of a particular digit. Again, VCL performs very well, and the image quality remains high for all the historical tasks. In summary, we proposed a practical Bayesian continual learning framework. The idea is to keep on updating approximate posterior and using it as the prior for future tasks. We demonstrated with Variational Inference that this framework works very well for continual learning. Lastly, let's talk about the need for the model to be able to fix its bad behavior. And interestingly, this can also be achieved via continual learning. But why are we interested in this problem? Let's start from a famous quote: "All models are wrong, but some are useful." Indeed, there's no way to avoid mistakes if the model is deployed for long enough time. But the model can still be useful for some other tasks that we care. So it's better to repair it rather than throw it away. Right now, this repairment process is mostly done manually by data scientists. which is costly and time-consuming. So we would like to automate this process, which will benefit a wider range of users. In this work, we assume that the model mistakes are mainly due to deficiencies in training data. For example, label noise is very common in medical data, and there are other data bugs like outliers and selection bias. To repair the model, we introduce a two-step framework as follows. Given the failure examples F in test time, first we find a subset of detrimental data points as the causes that contributes to the failures. And then we treat the model by removing the information about the causes. These two steps can be automated using continual learning. Let me show you how. In cause identification, we define a rating for a set of potentially detrimental data points C as the improvement of performance on the previously failed cases had C been absent in training data. There are two issues here. First, we have a combinatorial search problem. Second, we need to compute the updated posterior predictive for each C. Both procedures are extremely expensive. To solve the problems, we use the idea of continual learning, and the key idea is to learn new information from the failures and find conflicting cases in training data. In detail, first by manipulating Bayes' rule, we can rewrite the rating function R in a way that only requires one posterior update using the failure examples. Then we can apply Taylor expansion and obtain a linear time approximation to the rating function. Lastly, as the two exact posterior distributions are intractable, we just replace them with the approximate posteriors. Here, Q is the trained model, and the Q plus F distribution can be obtained using continual learning. These three steps address the two problems altogether, and the resulting approximation is practical to compute. Indeed, we can use any continual learning methods here, and we show that if we run one-step EWC update, then the resulting approximate rating is exactly the linear influence function. We can run EWC for a longer time, and this gives what we named EWC influence function that can be more accurate. Once we have identified the causes, then in treatment, we will remove the information of C from the model. This can be done by removing the likelihood factor for C from the current posterior. In practice, we updated the current model Q to the repaired model Q minus C by applying continual learning to the new task of minimizing the log likelihood on C. Indeed, any continual learning method can work, and we can also show the connections to various machine unlearning methods under the continual learning framework. Let's see an example on how this framework works. Here we consider label noise by adding wrong labels to digits 1, 6, 7, and 9. Indeed, the training model makes a lot of mistakes on these digits. We first test the cause identification approach with EWC, and indeed our approach can better find the right causes that correspond to mislabeled digits as shown on the right-hand side figure. Then we test removing the identified causes from the model. As we can see, the model's accuracy on failure cases is improved. But more importantly, if you focus on the red curves, the updated model with our approach also maintains its performance on other test data. This shows our continual learning method can achieve fixing error and maintaining performance at the same time. To sum up, we presented a continual learning framework for model repairment that subsumes many prior works. But more importantly, our work opens the door for adopting advanced continual learning methods in this new setting. In the paper, we have more results, including input noise and data poisoning, so check it out if interested. For takeaways, we discussed two requirements for trustworthy AI systems: reliable uncertainty estimates and the ability to adapt and learn in a lifelong manner. This can be achieved via Bayesian deep learning and Bayesian continual learning, and the approximate inference quality is key to these approaches' performances. In terms of future work, for better uncertainty estimates, as we mainly look at the uncertainty metrics computed on network outputs, I've started to spend more time working on capturing uncertainty in function space rather than in weight space. Also, as we are interested in AI-assisted decision making, we should also take Bayesian decision theory into account. One important aspect that I'm currently very interested in is to understand how to better present the model uncertainty to layman users who might not have much machine learning expertise. This is beyond typical machine learning, but I think it is important for enhancing our trust to these AI systems. For adaptive and continual learning, we are working on approaches that can repair other types of model failures. But also, it will be great if the model can detect failures and test environment changes by itself. And this needs improvement on auto-distribution example and change point detections. Again, Bayesian principles can be applied here. Lastly, although not mentioned in this talk, good representation learning and explainable AI are both important ingredients for better AI systems. Thanks for your attention. If you are interested in Bayesian machine learning, you can check out the 2 tutorials that I gave on the topics that I discussed today. Let me know if you have questions.